Okay. So, what we'll be discussing today is a continuation of what we were doing in the last class, and it is mostly based on electromagnetic waves and how can we, you can say, how does the waves change as it moves from one medium to another, and what are the characteristics that come up in the waves? How do a incident wave look like after it gets reflected from some surface and things like that. So, uh, this is a continuation of what we have been doing till now. Now, mostly what we'll discuss is some of the basic concepts of electromagnetic wave propagation, and then we'll try to solve some questions. And if you have some doubts, I'll try to address them. So, to start with, we know that what exactly is a wave? A wave is some function which has a temporal dependence as well as some spatial dependence. And as you can see here, it follows the wave equation. So this is in 1D. And here, as you can see that if you have a sinusoidal wave, suppose, then it has a temporal periodicity and a spatial periodicity, right? This lambda is the spatial periodicity, and T, which is the time period, is the temporal periodicity of your wave. And you can see here that for a wave which is propagating along maybe positive z direction, you can write it as some a cos kz minus omega t and things like that. And suppose if it is traveling in any arbitrary direction, then your wave vector, which is k, uh, comes up in the expression as k dot r. So you take the that's the most general form of writing the temporal dependence of a sinusoidal wave function. And then if it's in 3D, then what happens is your wave equation gets modified where you have del square operator coming up here, right? So now, keeping this basic picture in mind, what we see is that now if we talk about Maxwell's equations, which we had already discussed about in the last class, we know that in spaces where there is no charge and no current, this is how the Maxwell's equations look like, right? Now, you if you do a curl of E, and then if you use those use the formulas, what you get is something like this. Here you have make use of the concept that in free space where there is no charge, so rho is 0, then the gradient of E turns out to be 0. Divergence of E turns out to be 0, sorry. So what we then get is an equation like this. Similarly for B, we can get a similar kind of equation, right? And from here, putting the divergence of E and the divergence of B to 0, what we get is this, which is similar, or which is actually the wave equation, right? So that means the electric and the magnetic field components of an electromagnetic wave follows the wave equation. And here, if you compare it with the basic or the generic form, you see that this 1 by mu naught epsilon naught is actually root over of like 1 by root over of mu naught epsilon naught is actually the velocity of light, right? And that is what comes up here. So this again shows that light is an electromagnetic wave. Now, this is in free space or in vacuum, okay? And if you again look at the boundary conditions, what you see is from the case that divergence of E is 0 and divergence of B is 0, you can say that along the direction of propagation, your so you would get this, like along the direction of propagation of the wave, there is no electric or magnetic field. So your electromagnetic waves are actually transverse. Okay, so the electric and magnetic fields are perpendicular to the direction of propagation. And while in case of longitudinal waves like sound, you see that it's along the direction of propagation. And now if you use Faraday's law, which relates electric field or the curl of electric field with changing magnetic field, you can see that there is a relation between electric and the magnetic amplitudes, magnetic field amplitudes. And this is how they are related, okay? And so using this relation, if you know the electric field, you can actually get the magnetic field for an electromagnetic wave. And as you can see, they are mutually perpendicular to each other. So we know that the energy per unit volume in case of, okay, hi Amit. So what we are currently discussing is electromagnetic waves. So we'll first talk about what happens in vacuum, and then we'll move to matter, and then to conductors, and we'll see how one can express or describe this kind of waves as they move from one type of medium to another and things like that. Okay, so till now what we have seen is this is something we already discussed in the last class. So electromagnetic waves in vacuum, they follow the wave equation, and the electric and the magnetic fields are related by this relation here. And we know that the energy per unit volume stored in electromagnetic fields is given by this expression here. So this is the electrostatic contribution, this is the magnetic contribution. Okay, and now in the case of monochromatic plane wave, what you see is you make use of this relation. So this make use of the relation between electric and magnetic fields, and you get something like this. So this is your energy, you can say energy density, energy per unit volume, or energy density of your electromagnetic fields. Okay, and now if you calculate the Poynting vector, which is given as 1 by mu naught E cross B. Okay, so if you calculate the Poynting vector, what you see is S is actually mu times C into Z. So what is S? S is actually the energy flux that the wave carries with it. Okay, and as you can see, it's in the direction of propagation of wave. So all this is about waves in vacuum. Now, what happens when you have some wave and it goes and hits some boundary, some interface? Okay, so there'll be, so on this side, there's some property, medium property. Here, there's a different medium. So what happens to the wave, right? So a general way of thinking about it is if you start with a string and, if you vibrate the string, transversely, you would see that, and then if you have a knot somewhere, there'll be some propagation of your disturbance on this side, but there'll also be a reflection on this side, right? So similarly, in cases of waves, what happens is as the wave goes and strikes an interface, there'll be reflection and there'll also be transmittance. Okay, so if you have some incident wave, okay, what happens is you have a reflection. For suppose your wave is coming from z less than 0. Okay, so now at some later time, like at some point of time t equal to some non-zero value, what happens? You have a incident wave and you have this reflected wave. And as you can see here, you have k1z. Here you have minus k1z because it's propagating in the minus z direction. Okay, and then you have this transmitted wave, which comes up in the positive z direction. So in general, it's difficult to differentiate, like just looking at it, it would be difficult to differentiate between these two contributions, right? So they'll be together in this region, but there are these two parts, the incident and the reflected wave. Now, what happens at this junction, right? At this junction, your wave or the disturbance in your string or the wave propagation. So the wave should be continuous at this point, at the interface, right? At this point or at the surface of your interface. So what this tells you is this, right? So when it comes from some point and then it goes here, it should be continuous. And then for, so that there is no acceleration somewhere in this region, it's important that the derivative of f is also continuous, right? So these are the two boundary conditions that the waves satisfy. Any kind of waves try to satisfy as they move from one medium to another. Okay, and for sinusoidal waves, you can write it in terms of Euler formula, which is as given here. So basically, in our practical lives, what we talk about when you talk about waves, we look into the real part of it, but for mathematical simplicity, one can consider it as a complex quantity, e to the power I theta, something like that, right? So then you can write f of zt, which was something given here. You can write it in terms of the Euler notation, Euler's formula. Okay, and then in that case, you consider the wave to be a complex quantity. Okay. So now if you apply this, this is your wave, and then if you apply this boundary conditions, you get something like this. So this shows how this different amplitudes, the reflected amplitude, the transmitted amplitude, and the incident amplitude are related to each other. So you see how much quantity of your incident light is reflected and how much of it is transmitted, right? And that depends on what is the velocity of your wave in these two regions, right? If the two regions are same and the velocities are same, then obviously there won't be any reflection, right? So in that case, this term would go to 0. So this is a general way of looking into how waves propagate through mediums. Now, another aspect of electromagnetic waves is polarization. So we know that electromagnetic waves are transverse. So that means, suppose if you have some propagation of wave along z direction, it can have the electric fields can oscillate about, vertical. There can be vertical oscillations, or there can also be horizontal oscillations, right? So it can have vertical polarization or horizontal polarization, or it can also be in any arbitrary, plane, which like direction in the xy plane, right? So there can be an arbitrary polarization vector, n cap, which is actually some. So it can be, decomposed into some x cap and y cap. So basically, somewhere in the xy plane. But what's interesting and what's important is that always, because it's a transverse wave, your n cap dot z cap, so the dot product between your polarization vector and your propagation vector should always be 0. Okay, so this is the condition that one needs to satisfy for transverse waves. So now, depending on, so now if you think of electromagnetic waves, there will be electric fields which will oscillate in some direction. There'll be magnetic fields which will be mutually perpendicular to it, and they'll also have some oscillations. So in convention, we take into consideration the polarization direction of the electric field. Okay, so when we say that it has a vertical polarization, that we mean that the electric field disturbance or electric field goes like this. Okay, so it has a vertical polarization of electric field. Okay, so now if you have, so in this regard, there can be different kinds of polarization. So suppose if you have a similar kind of sinusoidal wave in x, and then some sinusoidal distribution in y, and then so what can happen is it can come up to a circularly polarized light. Okay, and otherwise, if the magnitudes in x and y are different, then it becomes an elliptically polarized light. So these things are similar to what we generally do for any kind of waves. It's not particular for just light. Like any kind of electromagnetic waves or any kind of wave-like disturbances. Okay, so now that we know that this is how the electric and magnetic fields are related in general, right? So if you take into account the real part, this is the Euler representation, and you can write it like this. Okay. So here, what you see is this is the case that what I was talking about, that K dot R. So this is the generalized formula. So here, wherever in general we are talking about Kz, considering that Z is your direction of propagation, but that might not always be the case. So this is the general form where, so if you have some, electric field specified, how do you find the K vector? So you have to look into the expression and see this K dot R term. So suppose if you have some coefficient into X plus some coefficient into Y, then you try to write it in terms of the K dot R terms, where X and Y comes from the R vector, and K, the coefficients are coming from the wave vector. Okay, so this is the general form. So if this is the electric field, your magnetic field looks something like this, which is mutually perpendicular to the electric field and the direction of propagation. Okay, and now this is something we have already been discussing. So we know this is what the energy is, and this is what the momentum is. Okay, so you can write the energy, you can write the Poynting vector magnitude. This is the momentum that the wave carries. So it's actually S, the Poynting vector, by c square. Okay, and the average of this. So it's important to do an average, because generally, like it has, depending on the frequency, it's the average of these quantities which actually makes physical sense. So here, if this average of Poynting vector is actually the intensity. So when we talk about intensity of light, this is what we mean. Okay, and this is the momentum that this is the radiation pressure, which comes up from the rate of change of momentum into like divided by area. So this is how the radiation pressure is related to the incident light. So in a way, radiation pressure is very important. This tells us that, light can exert pressure, light can exert force. And this lies at the heart of how optical tweezers and things like that have come up in research. Okay, and they have huge implications. Okay, so now we know about propagation in vacuum. This is about propagation in matter. So everything remains same. What has now changed is your relative permittivity and permeability. Okay, so now it's epsilon and mu, not epsilon naught and mu naught, right? And so in linear medium, we know that this is how D is related to the total electric field, and this is how H is related to the magnetic field. So you can write in terms of both H or B, or E and D, anything. So now you see that in this case, whenever it's in some different medium, now the velocity changes, right? So it's given by C by N, where N is your refractive index. And this is how refractive index is related to the relative permittivity or permeability of your medium. Okay. Okay. And similarly, the energy expression changes, the Poynting vector expression changes. So whatever is changing is just this mu naught to mu and epsilon naught to epsilon. Okay. What's important is this boundary condition. So this tells us what happens at the boundary, which separates different medium. Okay, and we'll just recap how these boundary conditions come up. So it comes up from these expressions. So if you consider some region which has some charge density, and then if you consider this kind of a pillbox, you can say from the first law that the perpendicular component of the displacement vector is given has this relation. So it's related to the charge, surface charge that is present on this sheet. And if that is not there, so there's no explicit free surface charge, then these are continuous. So these two, above and below, they are equal, right? So that's what you get from this law. Similarly, you get similar things from the divergence of magnetic field. So above and below a surface, the perpendicular components are continuous. Okay. And then if you look at this expression, so what this tells us is that here you can use the Stokes law. So you can write E dot dl over a closed loop and write it in terms of curl of E dot ds, right? And here you have another integration over a surface. And then you can compare. So what you get from there is, now if you consider this kind of a Gaussian region, and considering that this width is very less, it's negligible, then what happens is, in a way, you can consider that the net flux is zero. Net flux going through this region is zero. So there, this term goes to zero. So this tells us that the parallel components are also continuous. So E parallel to the interface are continuous across a boundary. And similarly here, you use this relation to say that this is how the parallel components of H are related to what is the surface current that can be present in on the interface. Okay, and if there is no surface current, then again this becomes continuous. So this is how you finally reach to this boundary conditions, which are very important in deriving the Fresnel coefficients and whatever that will come next. Okay, so now you have, we know whatever is the wave characteristics in vacuum or in different media. So now what we want to see is how, if you have some wave with some amplitude, how does it change as it passes from one media to another. Okay, and so this is about reflection and transmission at normal incidence. Normal incidence meaning the light is falling perpendicular to the plane of interface. Okay, so if this is your wave, which says that you have a plane wave which is traveling in the z direction and it's polarized in x-axis, so your electric field is along x-axis. Okay, and it approaches the interface from the left. So this is how it's coming. Okay, now it would give rise to some reflected light, right? And that would propagate in minus z direction. So your propagation direction is along z. So that propagates along minus z direction. And similarly, you have this magnetic field uh, that comes up from the relation that exists between electric and magnetic field in cases of electromagnetic waves. And then similarly, you'll also have a transmitted wave. So this is how the transmitted wave will look like. And it's important to note that here the wave vectors are all k1 because you are in the same region, right? The medium is same here. But in this side, the medium is different. So now your wave vector changes to k2. Okay. And then you apply all the boundary conditions, okay, which tells us that at the interface, your electric field components should be continuous. Okay. And if you apply those conditions, what you get, and this is the, you know, okay, so this is from 4. So by 4, I mean this condition, right? So from here, what you get is these two relations. And if you solve them further, you get this quantity beta. Okay. And this shows how it's related to actually the velocities of the waves in different media. Okay. And you can put it in these expressions to find the relative amplitudes of reflected and transmitted light. Okay. And this is just writing it in terms of velocities or refractive index. So this is the most uh, useful way of writing it, where you say that if there are two medium, N1 with refractive index N1 and N2, it goes from N1 to N2. This is how the reflected wave amplitude looks like. This is how it depends on the incident light. So this much quantity of the incident light is reflected and this much is transmitted. Okay. So from here, you can find the ratio of reflected light intensity. So whenever it's intensity, it's actually square of your electric field amplitude. And so it's a square of this term. And this is the transmitted light intensity. Okay. And if you add 2, you would see that R plus T, that is the reflection plus transmission coefficient, always turns out to be 1, considering that there's no absorption going on here in the medium. Okay. Now, if you have some oblique incidence, what happens there? So initially, when you had normal incidence, what we saw was, so there basically what we want to see is we want to see the parallel component and the transverse component of the electric field, right? So here the parallel component directly comes up because it's a normal incidence. But in this case, you'll have to consider how much of your, depending on the wave vector, how much of your electric field comes up along the interface. Okay, so that's what is different. So here again, the electric and magnetic fields, this is the, the incident one, this is the reflected one, and this is the transmitted one. So this comes directly from just wave equation. And now you apply this condition. So here it's important that because the wave, this is the same wave that's moving from one medium to another, the frequency remains same. Okay, so what changes is the speed, and so the wave vector changes. Okay, and so from there we can say that, if you look at this relation, ki and kr should be equal because they're in the same medium. Okay, and this is how they are related to kt, which is the wave vector in the transmitted region. And then this the boundary conditions should always hold. So the combined field of incident and reflected light and electric and magnetic fields, they should satisfy the boundary condition with the transmitted light at all times. So it should not depend on omega t, like e to the power I k dot r minus omega t should have be satisfied always at all points on the plane and at all times. Okay, so the exponents must be equal. So from here, what this tells us is, so time is obviously equal, so this goes away. So what's important is k1 dot r should be equal to kr dot r, and that should also be equal to kt dot r, right? And using that relation, so this is what is actually it's talking about. So if you use that relation, what you get is this. So more explicitly, this is what happens at the interface. Okay. Now, from here, what you can tell is it's interesting that you start with the Maxwell's equations, but now you are talking about the fundamental laws of geometrical optics. Okay. So what you see is, suppose if you say that from here that, if suppose x is 0, so if this term goes away, then you can say that all the y terms should be equal. Okay. While if y is 0, this tells us that all the x terms should be equal. So if we now orient our axis in such a way that your incident wave vector lies in the xz plane, so such that means your y component of the incident light is 0, which tells us that then all of the components, so y vector of both reflected and transmitted light will also go to 0. Okay. So this tells us that the incident, reflected and transmitted wave vectors, they are at the same plane. same plane of incidence, which includes the normal to the surface. In this case, it's the z-axis. So this is the first law of ray optics, and it comes up directly from wave equations. Okay. Now, if you look at this expression, you can say that, now you're taking the components. Okay, so your wave vector is the direction of propagation of light, and that makes an angle with the x, y, and z axis. So what is k1x? So it should be the sine theta I component, right? Depending on the angle of incidence. So if you look at those components, what this means is this should be equal, right? And now you know that k1 and ki and kr are equal. So that tells us that theta I should be equal to theta r. So this tells us the laws of reflection. Okay, so this gives us the law of reflection. Now, if you look at the other part of it, where it moves from one medium to another, so if you just take in the incident light and the transmitted light, what this tells us, this gives us a relation between the incident and the reflected angles and the medium properties, which is the refractive index of the medium. And this is what is Lenz's law. So fundamentally, we are talking about the different laws of geometrical optics coming from the wave equation and Maxwell's relations. Okay, and now these are some important concepts that here, if you're there are cases. So what can happen when when your refracted angle, so suppose your theta t, like this term, if the refracted angle goes to 90, so at that point the incident angle is called the critical angle. Okay, beyond this, so if you increase your incidence angle beyond the critical angle, what would happen? All the light would be reflected back to the denser medium, right? And this happens only when you move from a denser to a rarer medium, because in that case your light bends away from the normal, right? So only that case you can have the refracted angle to be 90 somewhere. Okay. So this is the definition of critical angle, which says that it's the incident angle where the refracted angle becomes 90. So if you use the Snell's law, you can find the expression for the critical angle. Okay. Basically sine inverse of n2 by n1. Okay. So now, if we looked into the exponential part. So we actually looked into this part. We said that the exponents should match. But now you also need to look at the individual components, right? And if you look at the components, this is what comes out from the boundary condition. So this comes out from the divergence of D being 0. Okay, so on this side and on the other side of the interface, this is how they are related. This is from the divergence of B being 0. This comes up from the fact that here, your parallel components are actually continuous, because just based on this relation, one second, just based on this relation, and the fourth leads to this expression, right? So this directly comes from the boundary conditions. Okay, now if you use the relation which relates the electric and the magnetic field, and you substitute the terms here, this is what you would be getting. Okay, and then you try to solve the. So what you get from here is the following. So you see that again, you see this is how the reflected amplitude depends on the different, the medium properties or the velocities of the waves in different media. And this much, so this is just the ratio of light that is reflected and the ratio of light that is transmitted. Okay, these are called the Fresnel equations. Okay, now this is important, that this tells us that if alpha is greater than beta, okay, so what happens in that case? Then this term and this term both are positives, right? So the reflected and the transmitted waves are always in phase, right? But now what happens when alpha is less than beta? Okay, so what is alpha? So this is alpha, right? Alpha is the relation which relates the, so it depends on the incident light incident angle of your, like, angle of incidence, okay, and the angle of transmittance, which is again related to the medium properties. So now what happens when alpha is less than beta? So in that case, this term becomes negative, right? So there, the reflected light is actually 180-degree out of phase with the incident light. So this Fresnel equations can tell us a lot about not only the amplitude, but also the phase and the relations between different amplitudes. Okay. Now, another interesting thing is that when alpha is equal to beta, what happens is, this term goes away, right? So that is called the Brewster's angle. So it's the angle where the reflected wave is completely extinguished. So from here, you can actually find the uh, expression for the Brewster's angle. Okay. Okay. So till now we spoke about vacuum, and then we spoke about medium with some epsilon and mu, different from free space. Now what we want to concentrate on is conductors. So in conductors, obviously you can see that there's a net conductivity, right? And so now you have a free charge, a free current density, and then you can write it as J equal to sigma E. Okay, so now if you use this relation here in the Maxwell's equation, you would get something like this. So this is an extra term that comes up. Okay, and considering that there are some free charges, this is what you get. Okay, and from the continuity equation, you can see that J is related to rho, right? So this in a way tells us how. So if you just solve that, what you get is this, right? So this is telling you how the initial free charge density is dissipating with time, right? And the characteristics time scale is given as epsilon by sigma. So this is like this talks about the fact, like physically, is that if you put some charge on a conductor, it would gradually flow to the surface or to the edges. And what is the time it takes for this charge to dissipate from the bulk to the surface, right? And so for a very good conductor, what would happen is sigma would be infinity. So in that case, your time it would take would be very less, right? So these are like approximations, ideal approximations. And so for a poor conductor, again, your tau would be much greater than the characteristic time scales. Okay. Now, here what we are concentrating on is not this transient character where you put some charge on the conductor and you wait for some time so that it goes to the edges. So that's the transient behavior. We are not thinking about or not interested in that particularly now. What we want to see is what happens after that. So after that, what would happen? Your rho would go to zero, right? There is no charge inside the bulk of your metal or conductor. So then your Maxwell's equation looks something like this. But you have this extra factor here, which was not present initially. This comes because of the conductivity of your material. And then if you use the similar mathematical relations of curl of E and all those expressions, and again here the divergence of E and B are zero. So what you get is something like this. So here again this extra term comes up in all these expressions. Okay. So now what happens is that this reflects in the fact that the wave vector is now a complex quantity. So this is your real part, this is your imaginary part. And what this is telling you is while the real part of your wave vector talks about the speed of light or the practical speed of light that you measure, or all this will come from this real part of your wave vector. But what this imaginary part is talking about is actually the absorption or the attenuation of the wave. How, in what rate does the wave gets attenuated. So this is the relation. Now these are just derivations. I will not go to to all the steps. But here, as you can see, if you have a very good conductor, what would happen? You can simplify this expression further, and then this is what you get. So it's important to remember this expression because this is what is generally used for any good conductors. Okay, and this relates your you can say the rate of attenuation like k with the conductivity and the material properties and the frequency of your wave. Okay. And what is 1 by k? So 1 by k is the distance it takes to reduce the amplitude by a factor of 1 by e, right? And that is called the skin depth. Okay. So now, so the attenuated plane waves, they also satisfy the modified wave equations. Okay. And so these are the modified wave equations where it's modified by this presence of this conductivity term. Okay. And then if you again look at this expression, so they would impose further constants, right? So this constraints come from this wave equations and the fact that they are always transverse. So now if you orient your electric field in the x direction, this is how it would look like. So here this added term comes up, right? It's now exponentially decreasing. It has an exponentially decreasing amplitude. Okay, and the amplitude goes as e to the power minus kz. So how will the intensity go as? So the intensity is e square, right? So it would go as e to the power minus 2 kz, right? And then this is how, electric fields and magnetic fields are anyways related. So it comes from this relations and the fact that they're transverse. So this is how you can write the magnetic field if you know the electric field. So now one thing that you have to look at is this term here. See, k here is the complex wave number. So what do you mean by complex? So any complex quantity, it has a magnitude and it also has a phase associated with it, right? So you can write k as something like this, some scalar quantity, like some quantity, not only scalar, like some quantity, and then you have e to the power I phi. So what is this? This is the phase, this is the modulus, this is the phase. So how do you find the phase? It should be similar to any vector, right? And this is given as tan inverse k by k. Okay, so tan inverse of imaginary by the real part. So this gives you the phase, and what gives you the magnitude? It is just root over k square plus I square. Okay, so if you now do that, this is your modulus, this is your phase. So if you look back, what happens now? So you can write k in terms of k into e to the power I phi, right? So there's this added e to the power I phi which comes up in the magnetic field, right? And that tells us that now the electric and magnetic fields are no longer in phase. So in conductors, what happens is the magnetic field lags behind the electric field. And by how much? By this factor. So which comes from this relation, right? So if you can measure estimate the wave vector, the real and the imaginary part, you can find how much the electric field, the magnetic field lags behind the electric field. Okay. And then you can also relate it to, by, so this is the ratio of the amplitudes of electric and magnetic field, and this is how it looks like. Okay, so finally, the electric and magnetic fields in some conductors would look like this. Okay, what's important is for any medium, okay, in general, the electric and so E and H amplitudes are related by this relation here. Okay, so what this tells us is that now suppose if it's not a conductor, then your sigma would be 0, right? So if your sigma is 0, what would happen? You get eta, which is called the wave impedance of the intrinsic wave impedance of the medium. So it would be given as root over mu by epsilon. So in any medium, if you know the relative permeability and the permittivity of the medium, you can find the wave impedance that the medium has. Okay, so now we'll try to solve some questions. So here it says that you have a plane electromagnetic wave which is propagating in a lossless dielectric. Okay, and this is how the electric field looks like. Now it's said that so these are the just E naught is the amplitude, K naught is the wave vector, okay, and they are constants, and these are the unit vectors along x and z directions. Okay, now what we have to find is you have to find the relative dielectric constant of the medium. So epsilon r you have to find, and you have to find the constant A. So just by looking at this electric field, okay, you can actually find the medium property, and you can also find A that is given here. So can you tell me how to proceed with this question? Like what should I do first? So what are the information that one can get from this expression of the electric field? Any idea? So if I just look at it, what should be the wave vector? So if I say that how does the wave vector look like? Can you tell me by looking at this expression? So it's important to understand when you are given some, some wave, some expression of some wave, some electric field disturbance, some magnetic field expression, what information does it tell us? So if you look at this expression, obviously a wave should have a wave vector which tells about the direction of propagation of the wave, right? And then it should also have some amplitude, and then it should have a polarization vector. Polarization vector means the vector along which your electric field is oscillating, right? So there should be a polarization vector, right? And then there should be it should also have the information about what is the speed in which the wave is propagating, right? So these are some of the basic informations that your wave expression should give you. So if you now look at this expression, what is a general way of writing a electric field? You write it as some E naught into e to the power I k dot r minus omega t, right? So now if you look at this expression, what do you think your k vector should be? So compare with, compare the exponent with this term. Sorry. Yeah. Anyways, you can understand, right? This is omega t. Okay, so now this part is interesting. See, omega t, you can, like, the t part is okay. So, right, you can compare it as, so you have, what you have is omega will be given as k naught into c, right? Now, what should be your k part? So from here, you need to find the expression for k. What should k look like? So what is the spatial part? This is the spatial part, right? So try to write the spatial part, and then what is r? So it is k dot r, right? These are two vectors, right? So r, what is r vector? It's like x into I cap plus y into j cap plus z into k cap, something like that, right? Here you have only x and z. So you can consider r to be given as x I cap plus z k cap, right? Then what should be your k? Can you follow what I meant? See, suppose if you consider r to be some, x I cap plus z k cap, then what will be your k? It should be something like 1 I cap plus root 3 k cap, right? Only then the dot product between them would give you something like that, right? Multiplied by k naught, obviously. Are you following? So by looking at this expression, you can actually find the wave vector. Because see, you need to find dielectric constant of a medium. So by dielectric constant, you have to somehow find the speed or something like that, right? So if you have to find the speed, so you can. So what you can do is you can start with finding the speed of the wave. Then you can find the refractive index. You can from there think of what your uh, dielectric constant should look like, right? So now in order to find the speed, what do you want? You need to find what the wave vector is, right? So this is how you can find the wave vector. Another thing that this tells you is the polarization vector. So this tells you that your electric field oscillates. It has a x component and it also has a z component, right? So now what I meant is, this is your electric field. So if you compare with this term, you get something like this, right? This is your k vector. And this is your omega. The omega meaning the frequency of your wave. This is the wave vector of your wave, right? So what should be the velocity? The velocity of any wave is given by omega by k, right? So from here, if you just solve that, what you would get is v is equal to c by 2, right? Now, what is refractive index? So if this is the velocity, you already know what your refractive index is, right? So in some medium, your speed of the light has reduced by 2. So then the refractive index should be 2, right? And how is refractive index related to the dielectric constant? This is how it's related, right? N is equal to root over of epsilon. So if you do that, you actually find the value of dielectric constant, right? Now, what is the other part? It talks about what should be the constant A, right? So now we know that, see, this is your polarization vector, right? Polarization vector is the vector along which your electric field is oscillating, and K is the vector along which your wave is propagating. Now we know for transverse wave, K dot n cap should be 0, right? So this is your K vector, and this is your polarization vector. So these two should, the dot product should be 0. So from here, you can actually find the expression for A, right? So is this clear to everyone? Guys, is this clear? Okay. So now this is another question which says that consider an electromagnetic wave at an interface between two homogeneous dielectric media of different dielectric constants, okay, epsilon 1 and epsilon 2. Now we assume that epsilon 2 is greater than epsilon 1 and there's no charge on the surface. Okay, so no charge on the surface, meaning your normal components of displacement vector is continuous, right? There's no charge on the surface. And this is your electric field vector, this is your displacement vector. Now, what are the two conditions? What are the inequalities that E and D satisfy in these two media? Now, this is a very qualitative question. So by looking at it, can you tell me what the answer should be? So try to think along the lines of the boundary conditions and how electric fields and displacement vectors are related to each other. Are you following the question? Like the question is clear to everyone? See, so what it's telling you is that what is dielectric constant? Suppose if you have some dielectric, what is actually happening? So then it would have some some way of altering your net field, because there'll be some induced charging that would happen, right? Now, when you say that epsilon 2 is greater than epsilon 1, if you look at how D is related to E, we know that D is equal to epsilon into E, right? So when your medium, when there are two homogeneous mediums, and then there's no extra charges anywhere, that means if your dielectric constants are more, then the displacement vectors are supposed to be more in that medium, right? So that tells you that your D2 should be greater than D1. Now, if D2 is greater than D1, we know that epsilon 2 is greater than epsilon 1, right? Now, talking about these two cases, what happens to the effective field, right? Like what is the electric field. So in cases of electric field, there'll be this polarization vector that would also come up, right? So there, because there'll be more polarization, and what basically happens is the polarization in a conductor. What happens when you have some polarization? It tries to cancel or negate the applied field. While in dielectric, the same thing happens, but it's not able to cancel it completely, right? But if your dielectric constants are more, then the effective electric field in that region is supposed to be less, right? So the answer is this. So here the dielectric, the displacement vectors are more in regions where the dielectric constant is more, but the effective field is less. Okay? Clear? Okay. So now this is another question where it now makes use of the of our discussion of how things happen, change when you have a conductor. So now you have this electromagnetically shielded room, okay, and you know that this is your frequency of light. The intensity of the external radiation that penetrates the room is 1% of the incident radiation, okay, and this is your sigma, conductivity of your shielding material. Now it says that its minimum thickness, so that only 1% reaches inside the room. What should be the minimum thickness of your shielding material? So what should you now make use of here? So you should make use of the fact that when there's some conductor, and because of this, so what is this shielding actually? So the electric field gradually, it attenuates in an exponential manner as it enters into a metal or a conductor, right? So you need to make use of that concept here. So what you do is, here it talks about intensity, right? So you need to use this relation. The k, that is the imaginary part of your wave vector, that gives us the rate in which your amplitude decreases, right? It decreases e to the power minus kz. So the intensity goes as e to the power minus 2 kz. Okay. So now what the question has given you is, you know I naught, how much percentage of I naught is I. So you already know that it's 1%. And you know your, so what you have to find is, you have to find Z, right? And for that, you need to find what is K, right? Now here what we'll do is we'll use this expression. So this is the expression that we said that for a good conductor, this is how K is related to the conductivity and the material properties, right? So these values are already provided to you. So if you use this relation, you find the expression for K. This is the imaginary part of your wave vector. And then if you replace it in this expression, you would find the value of Z, right? So if you do that, you get something like this. So this tells us that the minimum thickness of the shielding material should be around this value, so that only 1% of the incident radiation enters the shielded room. Okay. Okay. Now, this is another question which tells that, you have a plane electromagnetic wave which is incident normally on some surface, okay, and partially deflected. This is what naturally happens in most of the cases. Now, measurements on the standing waves in front of the interface shows that the ratio of electric field amplitude at the maximum and minimum is 5, right? So what it is telling you, that if you stand in front of the interface, so you have some interface, the wave comes in, okay, and then some part of it gets transmitted, some gets reflected. Now you are standing in front of the interface. Okay, so you have, this is your thing, okay, so now you have a reflected light here, and you have the incident light and the reflected light, and this is your transmitted light. Okay, now you are standing here, okay, and you see that the electric field amplitude has a maxima and has a minima, and the ratio of that is equal to 5, right? So what is the ratio of the reflected intensity to the incident intensity? So basically you need to find the deflection coefficient, right? So how do you do that? Any clue? So make use of the fact that you have this wave, there are two waves that are involved in this region, right? This and this. And they have different amplitudes. So this has a different amplitude, this has a different amplitude, but their frequencies are same, right? So what will happen from concepts of, the very fact that if you look at this, there's a maxima, there's a minima, sorry, there's a maxima, there's a minima, and then there's a ratio of that. This somehow reminds us of a optical phenomenon, right? When we are talking about cases when you have two waves, but they have same frequencies, right? So can you guys think of some optical phenomenon which involves waves of similar frequencies and then in a region, and then what they result in is sometime a maximum and sometime a minimum? Any idea? So what will happen? So what happens when you have different waves which are coherent? Coherent meaning they have same phase difference. So here, if they have similar frequencies and they are coming to like they exist in this region, so they're actually coherent because their frequencies are the same, right? So what will happen? They should interfere, right? So if they interfere, so so what will happen? There'll be some interference where there'll be constructive interference as well as destructive interference, right? And now you know the ratio of maxima and minima. So what this tells you that you can write it something like this, right? So if this is your incident light, this is your reflected light. It tells us that when you have a constructive interference, you would get something like this. They will add up, right? And this is the difference where you get a minima. And the ratio of that is 5, right? So now if you start from here, what you can do, you can just solve it, right? So if you solve it, what you get is a ratio between the amplitude of the reflected light to the incident light. And what is the square of this term? The square of this term is actually the ratio of reflected intensity, right, to the incident intensity. So that is what the question is asking, right? So the answer should be, it should be A, right? The square of this term. B. Why do you say it's B? See, this is intensity, right? What you got is the amplitude. Is that clear? Yeah, right. It should be in ratio of intensities is square of ratio of amplitudes, and it is given as 4/9. Okay. Okay. Now here you have a plane electromagnetic wave which is traveling along positive z direction, and the maximum electric field along the x direction is this. So this is in a way the amplitude of your electric field. Okay. Now the approximate maximum values of power that you have to find. Okay. Power per unit area. And so power per unit area is what? Power per unit area. That is energy per unit time per unit area. That's actually intensity, right? So you need to find the intensity and you need to find the magnetic induction B. What you are given is E, right? So what should be the relation that one should use? You have E, you want to find B, and you want to find I, the intensity. So if we go back and look at how things are related to each other, you would get something like this, right? So you need to find I, you know E naught. What is E naught? E naught is the amplitude of your electric field, right? That is given to you. You know the medium, I think it was vacuum, most probably. So now you know all of it. So you can find I, right? So if you use the relation, what will you get? So what is intensity? Power by power per unit area. And this is how it's related. So you can put those values, right? And this is what you get. So this is your intensity. Now, what is the magnetic field induction? So now you need to use the relation how electric field and magnetic field components are related to each other, right? So use the relation that curl of E is equal to minus del B del T, and consider that both the, 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 the time dependence goes as e to the power minus I omega t, and the spatial dependence goes as some k dot r or kz, the kx for electric field in this case. Okay. So if you start with that relation, what will you get? You'll get a relation between electric field and magnetic field, right? And this is something we have previously discussed. What is that? So this is something we have been using everywhere. See, this is something we have been using everywhere, right? So here, suppose if you, so this is for the conductors where you have the complex scale. Let us look at the simple case, right? We are talking about in vacuum. So, one second. So basically, this is something we have started our conversation with. Like this is your B. This is how B is related to E, right? And now what is omega? Omega is actually C into K, right? If it is in free space. And if it is in some different medium, it should be V, the velocity of the wave in that medium into K, right? So this is how the magnetic induction is related to the electric field amplitude, right? This is the magnetic field amplitude. So now you know E naught, you need to find B naught, right? So just divide it by the speed of light, right? So if you go back, you can divide it by the speed of light. And this is what you get, right? Okay. So this is another question which says that now you suppose that your YZ plane forms a chargeless boundary between two media with different permittivities. Okay. E left is to E right is given as 1 is to 2. If the uniform electric field on the left, so on the left, your electric field is given. What you have to find is the electric field on the right, right? So you have this media, okay, you know the electric field here, you need to find the electric field in this region, okay? And what this tells us is this is 1 is to 2. So this is here is 1, here it's 2, right? These are the things that are provided, okay? And your YZ plane, so this is like, suppose if you consider this along X, this is your X. So the YZ plane forms the chargeless boundary, right? So something like this. Yeah. So as the wave is propagating, you see that it's a chargeless boundary. So what would happen if you think of the first boundary condition? So the normal components of the displacement vector or the electric field will be continuous, right? Because there's no charge on the surface, on the boundary, right? Am I making sense? So when you say So what does that mean? So your D perpendicular here and the D perpendicular here, they should equate, right? So that means epsilon1 into epsilon left into E left should be equal to epsilon right into, okay, so you say A. Why do you say A? Can you explain? Feel free to tell what led you to this answer, because it's partly correct. I would say that it's partly correct, but there's one thing that you have slightly messed up. So it would be easier for me to, tell you where you went wrong if you say what led you to this answer. See, in yeah, tell me. Okay, okay. See, let us look at the solution. I think then it would make sense. So what I meant is, what are the different, so what we know the electric field in this region, we want to find the electric field here. So we need to use the boundary conditions that describe how electric field components vary over from one medium to another, right? So one boundary condition is what? It relates the normal components, right? And that tells us, so D normal above should be equal to D normal below. So you can say, sorry, I'll not write, I'll just tell, okay? Because this writing is. So what that tells us is E left into, like epsilon left into E left, just the normal component, should be equal to E epsilon right into E right of the normal component, right? And what do you mean by the normal component? The normal component of the boundary, right? So normal component of the boundary, that means what is the normal to YZ plane? The normal to YZ plane is X, right? So if you just now look at, yes. So now if you look at the X component, if you just look at the X component here, what is this telling us? So the X component of E left into epsilon left should be equal to epsilon right into the X component of E right, right? So if you do that, what should be your E right, like the X component? So what is this telling you? See, C into 1, right? C into 1 should be equal to what? It should be equal to 2 into the X component of E right, right? Sorry, wow. Yeah. The so the X component of E right, right? So that means, right, correct. Now it's making sense, right? So that means this is how your X component should look like. And why does the other two components remain same? It's because if you look at the third, if you remember the third boundary condition, it says that the parallel components of electric fields are continuous, right? E parallel above or left should be equal to E parallel right. So parallel means parallel to the surface. So the Y and the Z components should be same. So the answer is this, correct. Okay. So this is what it's actually talking about, right? If you equate, you would get something like this. So this is your answer. Okay. So now we look at this term. This is another question which says that, you have the electric field and the magnetic field in a charge-free region. Okay. Now, what is the average energy flow in the X direction? Your wave is propagating in X direction. Okay. But as you can see, you have these terms here, right? So these are exponentially decaying amplitudes. Okay. So what is the average energy flow in this direction? So when we talk about energy flow, what should we do? We should look at E cross B, right? Because this is what gives us the energy flux. So now if you do E cross B, you have to find the average of it. So you can do an average. So these are straightforward questions. So that would give you the answer. So the answer should be E naught square K2 by 2 mu naught omega. So this is your answer, right? Okay. Now here you have the electric field of a plane wave in a conducting medium. So because it's conducting, you have this exponentially decaying term here, right? And then you say that omega is your angular frequency, A is greater than 0. Now the phase difference between the magnetic field and the electric field. So we just saw that in conducting medium, your electric field and magnetic field, so the magnetic field lags by some phase, right? So now we need to find this phase difference for this question, right? So first we should look at what what does this wave vector, this wave like equation telling us, right? What is the electric field telling us? Okay. So comparing with with a generic form of electric field in a conducting medium, what should be the wave vector? Can you tell me what the wave vector should be? It's similar to the first question that we tried to solve. So for that, what do you have to do? We have to compare this section. So normally, what is the generic form? Cos of k dot r minus omega t, right? Here you only have z, so you can write it as cos of kz minus omega t. It's propagating along z. Okay. Now what should be k? It's straightforward, right? K should be 1 by root 3a, right? And now what is this term giving you? This term is actually giving you the imaginary part of your wave vector, right? This is giving you the real component. As I previously said, the real component talks about the speed or practically the speed of the wave or all these practically realizable quantities come from the real part. What the imaginary part of the wave vector tells us, it tells us about the attenuation that the wave undergoes, right? So that means this gives us the imaginary part, this gives us the real part. So now that you know both the real and the imaginary parts, can you tell what the phase difference should be? Think of this relation. Think of this relation. The magnetic field lags behind by the electric field, and this is the phase phi. And what is phi? Phi is tan inverse of k by k. What is k? K is the imaginary part, and this k is the real part, right? You know both of this. You want to find phi, right? So you can use this relation to find phi, right? So that's what is being done there. Okay, 1 second. I need to remove this. Okay. So what do? You do the following. So here, this is your imaginary part, this is your real part. So what is the ratio of that? Tan inverse of that ratio, and that gives you phi. So your phi is 30 degree, right? And we know that B lags behind E, right? So the answer should be this, right? So these are some of the questions that I plan to discuss. Do you have any doubt regarding any question? Okay. If you have some doubt, you can ask me. Okay. Okay. So if not, then let's call it a day. Okay. Thank you. Yeah. Yeah. Thank you.